wasn't very happy with how the lecture went last time, so I want to try to, but I was, part of the problem is I was trying to belabor a point that kind of should be belabored, but also, I mean, depending on how much you care, you can get really worried about it or not. So I want to move beyond it fairly quickly, but let me try to summarize slightly better what I was trying to say. So what I want to say is if you have this, we're in this situation, we have a single critical point of a Morse function on it. And I want to say that this, because I have a single critical point of index k, then this coordism can be understood as, first take a product on the bottom, take the bottom cross interval and add something standard. And that something standard should be determined by the dimension of the manifold and the index of the critical point. And then how you attach it is a little bit of extra data, okay? And it's also important. So that something standard is called a handle, or an n-dimensional k handle. And there are various different ways in which you can think about what this object is. Okay. So, so in general, this thing is, I have so an n-dimensional k handle. The most standard thing that you say is an n-dimensional k handle is bk plus bn minus k. Okay, so it's n-dimensional because these things add up. B stands for ball, right? And then it is, notice that this is not a smooth manifold, it has corners. Its boundary naturally decomposes into two parts. The boundary of bk cross bn minus k. I should have a little schematic here for what this is. Let's draw a picture of it. I like my picture of it. I think that is, this is just helps me distinguish the two factors. I think of one of them is long and one of them is thin, but that's not really that important. So this direction is bk, and then this direction is bk minus k. So some people like to think of it as a thickened up k-ball, k-dimensional ball, thickened up so that the total dimension is n. And then the boundary of it naturally decomposes as the boundary of this part across that, union this part across the boundary of that. So that's an sk minus 1 cross bn minus k, union of bk cross sn minus k minus 1. And these are two different parts of the boundary. Those are a little bit of color coded here. Blue. So this is the red part here. That's the boundary of this factor crossed with the other factor. And then the blue part is this stuff. That's the first factor crossed with the boundary of the second factor. Okay? And then, so in this picture, where you're supposed to see that handle is you're supposed to see, you go up to some height, and this is just a product. And then the handle goes right over the top of this critical point. There's the handle. Okay, the handle is factored as a k-dimensional ball. And that k-dimensional ball, where is it coming from? It's coming from this local model of the Morse critical point of index k, and it's the descending part of it. Right? K is the number of minus signs in that standard model. So that's why, so this is this here is your bk, and then this direction is the number of ascending coordinates, where the number of pluses, and so that's your bk, bn minus k, I'm sorry, right? And then what you want to do is you want to think of this whole thing is built by attaching this handle. How do you attach it? You attach it along the red part. Okay, part of the boundary. It's not glued to this thing along the entire boundary. It's only glued along this thing, right? And pick it back. Okay, so that's why this part is typically called the attaching region of the boundary. So that's the part along which you attach the handle, and then the other part runs over here, and that's the part that it doesn't get along. I don't know how, this is quite a standard, I call this You know, as opposed to the attaching region, this is the free region. And then the observation is, well, this is, okay, well, how do you attach such a thing? So what does it mean to attach a handle? So attaching, attaching a handle, k cosine n minus k, to, so let's put, I have a pre-existing cobordism. And then attaching it to a pre-existing cobordism means you choosing well, let me say what it means to attach it to a product. To 0, 1 cross M0 means, yeah, already I've gone and I've called this 0 to 1 rather than 0 to f of p minus epsilon, which is what I was calling it last time, of course it doesn't matter. Means you choose an embedding of the attaching region. And the attaching region is xk minus 1 cross bn minus k into the top part of the cobordism, into 1 cross m0. Right? And having chosen that smooth embedding, then you glue, right, and then you glue using this embedding. Which, I won't write this down, but topologically that means you take the disjoint union of the handle and the cobordism, and then you mod out by the equivalence relation, which anytime you glue two spaces together by a function, that means a disjoint union, mod the equivalence relation that a point is equivalent to its inverse. Okay? However, that can be done, that actually determines a unique smooth structure, and that's another story. If you want to know a little bit, if you're bothered by those details, right, I would recommend this book by Krasinski, called Differential Manifolds, which does discuss carefully what it means to glue manifolds together along boundaries or parts of their boundary and so on. And that has some of the technical details. And in particular, one of the problems with this is even if you take the standard approach to gluing smooth manifolds together, you end up with something with corners, and then, so then you would say, and then round corners, or smooth corners. And that's the most fishy part. But Krasinski talks about pretty carefully how to explain what that means, and I won't say too much more about it. But smoothing corners then means you sort of do some kind of canonical smoothing there. You have some canonical model for what's happening in this local neighborhood of these corners, and you can canonically smooth it. And then the final thing to observe is the rest of it is again a product. Now, arguing that the rest of it is a product, there's various ways to do it. Notice that if you want to use the original Morse function, the problem is that the original Morse function has a level set here, and your standard argument would say that this is a product, right? But if there are various things. Milner's approach in Milner's book on Morse theory is to make a new Morse function which has a level set that goes like this, sort of by interpolating with the original Morse function and the new and the original Morse function and the original Morse function with a sort of bump in the middle that pushes it up. That's one approach, and then you can prove that this is a product. I don't want to say anything more about that. And so this is, so then you want to argue that anytime you have a critical point of index k, you can zoom in on the local model and find inside there bk cross bn minus k attached to f inverse of f of b minus epsilon. Now, the other thing I was trying to argue was that you could instead describe, so alternate. And then the key point is that this is a completely standard object. It's not, this object is not in your manifold. You're setting up a diffeomorphism between your manifold and something built out of a product and this standard object. So this standard object just sits as a subset of RA, right? Not a subset of your manifold, but then you find a subset of your manifold diffeomorphic to it. Okay, so alternate definitions of handless key thing is that a handle should always be an abstract object defined independent of any particular manifold, and then you always have this theorem that if you have, anytime you go from below a critical point to above a critical point, that corresponds, the result is diffeomorphic to attaching this standard object. And so, so the one that I was trying to do is, I just do the schematics since I flavored perhaps more than anything else last time, is you take your, so this is Rn, it's going to be a subset of Rn, but it's not BK cross B minus K, it's slightly different. Topologically, it's homomorphic to that. And this is where you take your, it's this thing with, it's this coordism with its own corners. Okay. So it's, remember, if this is x1 up to xk, and this is xk plus 1 up to xn, right? So then, if here, I'll use somewhat the same color scheme, right? Sitting right here, I take a small neighborhood. So first of all, the two dots are really the unit, or a unit or epsilon radius sphere inside the x1 up to xk space, right? So that's an sk minus 1, and then I thicken it up inside that, I take a neighborhood inside the submanifold f inverse of minus 1 or f minus epsilon or whatever. And then that's, then I'm going to put some corners on here, flow from the boundary of that all the way up to f inverse of epsilon, and finally at the top I'll have this thing here. So the red here is supposed to correspond to the red there, and the green there. If I want to see this inside here, I could just chop the corners over there, and this is totally more than the same thing. Okay, so anyway, so then that's this alternative thing, and this has a nice feature that it itself, the handle by itself, is a cobordism. But then what you want to say is, so the picture for this then is that you're trying to understand how this object is built, and so I would say this object is built with 4 parts, a product below, a product above, and then I'm going to have red here, red in the back, blue here, so that becomes my handle. This becomes my index K handle. But the point is, then what you want to do is you want to say, okay, you start with a product, you attach this, and simultaneously on the side you attach a product coordinate. So then you have 2 coordinates with sides on them that you group together, and then you finally have another product coordinate. So depending on how you like to set things up, that might have its advantages. And then the other alternative definition I work. Any questions? Huh? Yeah.
So I'm having a little trouble picturing what happens. Okay, so you glue this handle on and you have this product.
Yeah.
But it's like a product of what exactly?
Right, so it's what okay, let me do it over here. It's a new, okay, after you attach a handle, then either you attach it this way, in which case you glue the handle on, and then you know, in the complement of this level set, you attach a product as well, and you get something, and it's some new manifold.
And I guess my question is like what?
Right. So we're going to talk about that.
Okay.
It's a new codimension 1 submanifold of this original manifold. Okay, and we will talk about how its topology itself is determined by the topology of this manifold and the attaching manifold, and that process of getting a new manifold from an old manifold by building this cobordism that seems to get is called surgery. And so if you think about what you've done is you remove something, the red stuff, and you replace it with the blue stuff. And the red and the blue have, I mean, the other thing to notice about these 2 pieces, right? What's the boundary of sk minus 1 cross bn minus k? it's sk minus 1 cross sn minus k minus 1, which is the same as the boundary of this. Of course, obviously they have the same boundary because they deal on the thing. So you're removing something which has a certain sphere cross sphere boundary and replacing it with something else that has the same sphere cross sphere boundary. Okay, and that's general surgery. And we can talk about that. But another way is, I mean, in the original setup, I just said, you know, x is a coordinate from m0 to m1. So you sort of, in principle, maybe knew what m1 was already or something. You want to understand the coordinates in itself. And then the top part is just m1 crossing. But that, I mean, it's a different question.
You're skipping something that needs to be
We're coming,
proven,
yeah.
right? That, like,
Which is what?
you actually get M1 on the bottom.
Well, originally I said, suppose I just have x as a coordinate from m0 to m1, and that's given to you. It's something, whatever, you know that, and f goes from x to 0, 1 with a single critical point. And then the question is, really, rather than, I'm not asking the question, how do you understand m0 and m1? I'm asking, how do you understand x? What is the topology of x? But
it seems like you do something in the middle.
yes, you
right?
do something in the middle.
And then you claim that you have a product above it. So in particular, like,
My argument that you have a product above it is just flow along the gradient vector field. So I
so
do,
you sort of
I
get
do
to
something in the middle and I
products
get to
of
something, right? I mean, right, so I get to this manifold, whatever it is, right? But now, from here to here, I have a Morse function with no critical points.
So it's a consequence.
Therefore, it's a
that
product.
is M1.
Therefore, this is diffeomorphic to that. That's it. Now, the argument I'll set the other. So the other picture I wanted to do was to say, so the other alternative picture. Right at the bottom, there's the attaching region, and the other standard model. And then I wanted to do something where the blue just sort of comes like this.
This is the bump function.
This is the bump function, I think. But it's actually also, if you look at Milner's argument, it also works that way. So this is now something, this is some, okay, I don't want to go over again. Well, actually, let me say just a little bit interrupt and so, yeah, let's do this. So this is another model of a handle. So first of all, adds what it would look like. So it corresponds to sort of taking this picture and adding like a little flange there. So that when you want to glue that handle to something, right? So if I want to, I mean more abstractly, if I had say a disc and I want to glue this handle to it, I would be gluing it with it. It's just a disc cross disc, like interval cross interval, I'd be gluing like this, but if I glue it with the flanges, then the result is automatically smooth. Okay? And so what is this object? One way to describe it then is to say, let me finish what I said. So I can take, but rather than think about my setting being in an abstract manifold X, let me just focus on, I'm trying to construct a canonical object called an n-dimensional K handle. So let me say I'm in Rn, and my function f is just, sum of the minus xi squared, sum of the x squared of k, n, okay? And so now I have the standard gradient vector field. I don't even need to say gradient with respect to g, I'll just say grad f, right? Consider grad f. Gradient field for f. And then I want to, let me just, so this, let's call this, I've got this, well, the first thing would be how you would define this red submanifold, but it's f inverse of, it's a neighborhood of the sphere inside the first K component plane, and its neighborhood of that, it's a disk neighborhood of some radius inside F inverse of -1. We can just now just say this is F inverse of -1 and F inverse of 1. Right? And so then this would be a sphere of radius 1. Right? And so then I could just take some maybe radius half or whatever. Okay, I don't want to put it at that point, but just call this thing, we'll just call this thing S K minus 1 cross E N minus K, right? And so then I can take, in fact, let me do something, yeah. So then I take, I let what do I call my function, tau, okay? I'm just going to go from sk minus 1 plus bn minus k to 0 to infinity.
Is it the union of the thing that's the...
What's that?
Is it the union of the thing that's the S?
The whole.
K minus 1?
Yeah, it's like all the thing.
Okay.
Oh, you mean I should just go, sorry, just keep going?
No,
Like the left side.
I mean...
Yeah, the left side too,
Okay.
yeah. Because really,
It's like an S.
Right.
this is
that's like an S.
right?
Yeah.
Okay, yeah.
Okay.
You know, it's a good example to try to get to is 4-dimensional, R4. So this really is 2-dimensional, and this really is 2-dimensional. So this is really, and say k equals 2, right? Then this, k is 2, and n minus k is 2, right? Then this is 2-dimensional, this is 2-dimensional, so this is a circle, and this is a circle. So this is time to get to F inverse of 1 along grad f. Any questions on that function? You know, it goes to, it's infinity precisely along sk minus 1 plus 0, right? And then I take mu equals a bump function. I'm going to say in the dk minus 1, bn minus k factor. So it equals 1, it's going to equal, let me, right, so it's going to take the value 1 here, and take the value 0 here, and go from 0 to 1 along here, right? And then I take, and then I let my handle, and then the handle is closure of forward flow lines for grad f at time mu times tau starting at and so that's just, you're gonna, outside something you don't flow at all, and here you flow for some time, just approach a circle. Okay? And that produces this thing that's just naturally smooth. And you're just interpolating from this level set to that level set. Okay? And now, so you can also find this naturally embedded anytime. So that's something that. Well, you might say, what if I chose a different bump function, et cetera, and you want to argue that the result of attaching this object to maybe one bump function or another, it doesn't matter, they're diffeomorphic, and that's not that hard to argue. And the picture in the actual embedded manifold should be that. So here's, again, to address your question about how do we know the top is a product, right? We want to think of it like, I've got this coordinate neighborhood in which I've done something nice, and I've picked out, so now the picture here should be that I've got this descending k-dimensional disk still in there from the coordinate neighborhood at this level. Then I've got this sk minus 1 cross bn minus k, and then I've got this handle that has this naturally smooth corner, something like that, and this is my So immediately upon attaching the handle, the result is smooth. Okay, and now what about the rest being a product? So what I would argue now is that I can take the original gradient vector field. Oh, so on this part here, I want to argue, so why is this a product?
So there's some limit that says like if I have a covariism that has no critical points, then I'm a product.
We proved that already.
Oh, that was
However,
there.
the only technical point I want to make is this thing is not presented to us as a coordinate with a Morse function. The thing that's presented to us as a coordinate with a Morse function is from here to here. Okay, so how do we know that from here to here we have a product? And what I claim is we still have a gradient vector field, right? But the extra advantage to it is that it's transverse to, do I switch colors?
Yeah.
Yeah, you just kind of.
So I switched colors anyway. We still have a gradient vector field transverse to this new boundary, and it's still nowhere zero up here, and it's transverse to this boundary, which means it's just going to. Well, you can make an argument that it will flow all the way up to here, and so again, flowing along that gradient vector, real normalizing appropriately, you can realize that it's a problem. That's it. So you use grad G at the end. Even though that's not even though the Morse function is not constant on this, you've done it. So that's the extent of the technicalities I want to give you. If you ever care about it more, you can play around with those different ideas. From now on, I'm going to say handle is disk cross disk, corners smooth. Okay? And we're going to look at examples. And there's one other thing, which is maybe before we get deep into examples, we should look at the case about the general setting where, what about k equals 0 or k equals 0? Well, in that sense, actually, these pictures are still sort of schematically true. It's just that this direction is 0-dimensional if k equals 0, right? And so all it means is that everything's increasing in this direction, and you still, well, you end up having, what about b? So, what is bk cross bn minus k? That's just b0 cross bn, right? In the case where k equals 0. And so b0 is just a point, and so all it's saying is you've got a point across, everything's having an n-dimensional direction, everything's increasing, and so this is really just well, they're all homomorphic to balls, but this one actually is a ball. And what is it attached along? That's the only subtlety. It's not attached along anything. So the convention is, so attaching region is, well, it's quote unquote S minus 1 cross Bn, but S minus 1 doesn't make any sense. By convention, that's the boundary of the zero ball, that's an empty set. So I'm going to give you examples shortly, and hopefully it makes more sense. And then for k equals n, we have bn cross b0, and now the attaching region is an sn minus 1 cross b0, okay, and the free region is nothing. So let me give you the simplest example of both of those phenomena at once. So consider simplest example of all. Let's say S1, standard embedding in S1 and R2, right? Here it is. Okay, take the normal height function, we get our Morse function, right? And then I can take, so this is minus 1 to 1, right? So I can temporarily think about, I want to divide, this has two critical points. Okay, I want to divide this into two pieces, two coordisms, each of them with just one critical point in it. Okay, so I can naturally divide it into, say, so these are critical points, critical values, and then I'm going to divide let's think about going from -2 to 0, right? And this is f. So what about f inverse of the interval -2 to 0? Okay, that's a cobordism from what to what? It's cobordism from the empty set to 2 points. Okay, so that's this. Okay, equals cobordism from nothing, right? I never said that. I mean, you might say, why isn't that a cobordism from a point to a point? But we're sort of, when you have a boundary of something, and you say it's, when you have something with boundary, you say it's a cobordism, you're automatically choosing, when you say it's a cobordism from, that you're choosing a partition of the boundary components into some that are at the bottom and some that are at the top. This manifold could just as well be thought of as this, but it's not in this case, it's not a response function. So the bottom is the empty set, and the top is 2 points. Okay. And then, so we're supposed to take the empty, just following blindly the prescription, we take the empty set across an interval, which is the empty set. We attach that using a gluing map from the empty set into 1 across the empty set, right? And we attach B0 across B1 to that. So that just means we just manufacture a B1 in the middle of nowhere. That's all we do, okay? So attaching, so therefore attaching 0 angle means create, in this case, B1 nowhere, and there we go. That's all we do, right? And then when you get to the top, so the other f inverse of 0 to 2 is this, right? Same thing, but now this is a cobordism from 2 points to the empty set, right? So you take equals, so I take 2 points across an interval. That's the first thing, right? And 0 across an interval. And then I attach to it union a 2 handle, which is union a 1 handle, a 1-dimensional 1 handle, which is B1 cross B0, attached along an S0 cross B0, attached along, the attaching region now is S0 cross B0, which is 2 points, and I need therefore an embedding of 2 points into 2 points. That's the okay, so that's sometimes low dimension is more confusing than necessary, but that's just to sort of settle it away. And you can do the same thing if you can think about it yourself, what happens if you have a 2-sphere, etc., or any dimensional sphere. So more of the point is any sphere is a union of 2 Sn equals 0 handle, 0 handle, n handle, because you can put, so with that, when I say 0 handle union n handle, I mean you attach a 0 handle to nothing, and then you attach an n handle to the top of that. By the way, there is a not entirely trivial theorem which says that, which I won't prove now, I'll use it later, that if x is closed and x, and there's the same Morse function, f from x to r, exactly 2 critical points, then f is homeomorphic. I'm just going to that probably, to attribute that theorem to? It's some sort of
it's in Mulder's book, but that's Mulder used that in these exotic spheres.
That's right. So there are examples of
How about then X's?
X. There are examples of 7-dimensional spheres that there's examples of 7-dimensional manifolds that have Morse functions with 2 critical points, a single min and a single max, which are not diffeomorphic to S7. So anyway, so more interesting examples than that. Oh, well, the other thing is, if I take, again, just sticking for one dimension for a second, if I take something like this, right, then I can also say, suppose this has 4 critical points. So first here's a 0 handle attached to nothing, right? And then I have another 0 handle. And so, of course, when I attach another 0 handle, that just means, I've got this space, and then I just create another, right? So they just attach it to nothing. That's another 0 handle, and then there's a 1 handle, that level, and then another one. Okay? So you could get a classification of 1 manifolds by thinking about the different ways 0 handles and 1 handles can be attached together. So let's go to direction 2. We have 0 handle. Now we'll draw pictures of it. 0 handle is B0 cross B2, and this. A 1 handle. But let's go back to our color coding. But let's see if I can actually remember. So what did I have? Red is supposed to be attaching, and blue is the free region, right? So this has only free region, right? Right? And then the 1 handle is what I read, B1 cross B1, and that's integral cross integral, but I always like to draw the first factor longer than the second factor. So there's the attaching region, free region, and then again, B2 cross B0. So when you attach a 2 handle, you've got to attach it along the entire thing, right? So that draw a picture of a torus and see these things. So you draw a standard Morse function on a torus. You're going to see first a 0 handle. Then you get a critical point. Well, okay, then what we would say is then there's a section which is a product. Well, let's stick to that language for a little while. Later we'll stop talking about the product. There's a product, right? And then there's a 1 handle. And I'll go over here as I times, so that goes. Just drop that. Okay, so there's a 1 handle that goes up and over. And so that's got there, here, and there. And then there's another product, right? So there's your 1 handle. And there's this other product. Symbolize that with lines. And then we have another handle which goes somehow the other way, right? So it's another 1 handle. We got there, and then another product. And finally, the 2 handle at the top. And this is also 1 handle there. And finally, 2 handle at the top where they all. Okay, and that closes it up.
So is there like a choice when you glue these things whether you take the orientation preserving orientation preserving?
Right. So we're gonna so So what you're jumping ahead to now is the question of how, I mean, and this is related to your previous question, right? How, so you can, I'm still taking the approach of, I've got some manifold, I'm drawing some manifold you already understand, I'm trying to decompose it, right? But the natural thing to jump to is, let's start building manifolds and think about the different ways we can build manifolds.
Like, those
Okay.
are the only questions, yeah.
That's well, for one handles, so to jump ahead to what you're saying, what you want to think, in principle, at the moment, what we know is that things are determined by this embedding of the attaching region. When you attach a handle, the diffeomorphism type of what you get is determined by the embedding of the attaching region into the level set just below the handle. Okay? Now, a moment's thought will show you that actually it's only determined by the embedding up to isotopy. Okay? If you move that embedding around by an ambient isotopy, or by an isotopy of embeddings, you won't change the diffeomorphism type of what you produce. Then you can say, well, these are embeddings of spheres cross disks, so thickened spheres into manifold. What determines the isotopy class of embedding of a thickened sphere into a manifold? And that's, right, so in this case, when you're looking at thickened S0s, the only thing that you care about is the orientation, or in this case, there's something subtle here, which is that my level set has two components. And another thing that could have happened is I could have attached this one handle there, or I could have attached it to both boundary components, right? Suppose I had done the other thing, attached it to both suppose I attached it just so its feet landed on this single boundary component. Then actually the new boundary would have three components instead of one. This is an example of surgery, so that the new boundary you get does depend upon how you attach it. And so if we had three components, then we couldn't cap off with a single two handle. That's another example. Okay, but the other thing to observe though is when you attach a two handle, right? As long as you tell which component you're attaching it to, that's all you have to say. It's just as long as that component is a circle, boom, that's it. So your top dimensional handle, as long as you know that the level set up here is a sphere, you can just say cap off with an N handle, and that's, you don't have to say anything more about that. As long as you know it's diffeomorphic to Sn, you understand the diffeomorphism, you say by that diffeomorphism.
So if you start with something that's oriented,
That's right.
then you can always pick orientation preserving, doing that?
Yes.
Like,
Yes. So I'll say that those things I think you can figure out yourself, but it becomes a little more interesting when we move up a dimension to other and start thinking about other index handles. So I mean the question that we're talking about here is what determines the general question is what determines an isotopy class of embeddings of some sk minus 1 plus bn minus k into some n minus 1 dimensional manifold, right? The n minus 1 dimensional manifold is here. And so if k equals 1 and m is connected, then, so this is, you just have to think about it on your own, then orientation is the only issue. And if you do it one way, you will construct a non-orientable manifold. If you do it another way, you will construct an orientable manifold. Local, right? But there's one way that inevitably puts an orientation reversing loop in the manifold, and that's it. So there's one way that forces you to end up with an orientation reversing with non-orientable manifold. So if we know, for example, that we never want to think about non-orientable manifolds, right? Say we didn't agree once and for all, never to discuss them, then there's nothing to be said about attaching a one handle. But there's some subtlety in this argument that orientation is the only issue, and we may come back to it later. But let me keep going with the examples. Dimension is 3. Right? So 0 handle is 0 cross B3. So that's, I can still draw a picture of that. Solid ball. But the entire boundary now is blue. Right? One handle, B1 cross B3, B2, sorry. So I'll draw my B1 long and my B2 skinny. So then the outside of this long tube is blue and the ends are red. Actually, two handle, it looks exactly the same, but I'm going to draw it differently. I'm going to draw the B2 big and the B1 skinny. So that's a B2 is a disc, so it's a fattened up disc. And then my blue is the top and bottom, and red is the sides. And finally, my 3 handle is just a ball again, solid ball, but the entire boundary is red. Now, suddenly it's much harder to draw pictures of closed three-dimensionals. Okay? But this gives you some idea how to begin doing that. And so, now I'll just do something dumb for sort of one example. I'm going to draw an example, and then something built. Three-dimensional handles. So let me start. So if let's say a closed three-manifold, it's going to have one thing that perhaps should have been emphasized. Any closed manifold is coordinated from the empty set to the empty set. So any Morse function on it, we'll have to have a minimum and a maximum. Minimum's got to be index 0, maximum's got to be index 3 in this case. So it's got to have a 0 handle, it's got to have a 3 handle. Okay? It might have more than one 0 handle and more than one 3 handle. Maybe we'll do an example like that. Okay? So I could have, so just let me random example. Maybe it's got 2 0 handles. So here's one of them. So I got a 0 handle. And maybe another 0 handle. One thing that I haven't recorded here is, in principle, those 0 handles one might be below the other, right? But I don't care for this construction, but in later contexts, we may actually want to record stuff like that. Now I need to, let's say there's one handle. Maybe there's a couple of one handles. Maybe one of the one handles might. So now one handle is supposed to be this object, glued by embeddings of those red ends into the boundary that we currently have. Well, technically, I'm supposed to now attach to this the boundary of this object across an interval, but I'm not going to draw that. Okay? So then I can take a one handle that might, for example, I might have one handle that goes like this. Okay? So there's red, and then more blue. I might have another one handle that goes maybe from here to here. Right? One phenomenon you'll notice then is that topologically it was kind of dumb to have this 0 handle and this 1 handle, right? And that corresponds precisely to this cancellation of critical points that we saw earlier. What this means, if you have a 1 handle connected to a single 0 handle and nothing else, it means you can modify the Morse function so that the 2 critical points disappear. So, by the way, you can also sort of, if you want to see critical points in level sets, in the middle of each of these index 0 in the 0 handles is a critical point, a minimum. And the level sets are expanding spheres around that, right? in the middle of each of these one handles is a critical point. And the level sets are, these level sets eventually become sort of have little fingers that move in, right? And then those fingers come together, and you get some level set that is a cone-shaped thing there, and then expands out. So you get some sort of interpolation from this, these two spheres up to this new boundary, which is a genus 1 surface. Let's see, how could we cap? We can't cap this off right now. We cannot attach a 3 handle. Why not?
So the boundary is.
The boundary is not S2. The boundary needs to be S2 in order to attach a 3 handle. We can make the boundary S2 just, for do something quick and finish the class by attaching a 2 handle, say along thickened up. Picture's out of control now, right? But the 2 handle is, this thickened wedge here, right? So I can, sort of hazard a sketch of it, right? I'm just taking this thickened up, this bowl, right? Thick bowl, and I'm attaching it down like this. Okay? You'll notice now that the new object really does have a sphere boundary. Topologically, it's a sphere over here, and this hole in its genus is now capped up. Actually, what that means also is that this one handle and this 2 handle cancel. And so I will end, then you can get a 2 sphere and attach. So what you would typically do is then say, union of 3 handle. So you draw some picture up to the point of the 3 handle, and then you say union of 3 handle, because you can't draw that in and close everything off. Right? So I'll just end with, what my advisor was famous for this particular example. Understanding the way in which this 1 handle and 2 handle cancel, he would always say is like roof of a convertible. Okay, there's the there's the 1 handle here, right? That's the frame of the convertible, whatever. And then there's the 2 handle that goes up over it and then along the bottom. So the table is the original 0 handle. Here's the 1 handle, and then the 2 handle comes up and over like that. And then that's like the roof of the convertible, and then it folds back down. And you might, once the two of them, if you just have this, this frame or whatever, something interesting topologically is happening. But as soon as you attach the 2 handle, it folds back down, and it's not there. So that's cancellation of a 1 and a 2 handle. And you could also think of that as a cancellation of the corresponding critical points. So we will continue these examples, talk more carefully about what determines the isotopies in general, and start. Let's spend some more time in 3 dimensions.